Hello, it's Scott Manley here. Today I want to talk to you about small satellites, itty bitty satellites. You've probably all heard me talking about CubeSats from time to time, although the spell corrector on my laptop keeps correcting it to cubist no matter how many times I type it. Regardless, you know that CubeSats are sort of the entry level, right? They're what universities build and launch when they're doing baby's first satellite. Now, CubeSats are 4 inches cube, right? That is the basic cube size, but you can make them larger by bending, merging the cubes together. So you'll have a 2U CubeSat, which is 2 of them. You can have 3. That's the size of the Dove satellites that were used by Planet Labs early on. You can even have a 2x3 version, 6U CubeSat. That is the size of the satellites that NASA sent to Mars. The Marco spacecraft, there were 2 of those, and they were able to go into deep space and actually send data back from their flight. And then you have like the 2x2x3, that's a 12U CubeSat. That's what like a Capstone spacecraft is that is currently orbiting in near rectilinear halo orbit, and by the sound of things, it may be the king of that orbit going forwards. But of course, those are the size that everyone builds. They've become a standard. Actually, they originally started like in 1999. A couple of researchers were looking at nano satellites, and they sort of ended up coming up with this informal standard, which it has become ultimately a supported standard. And there are many vendors who will take your CubeSat, they will integrate it onto their launchers, and they will launch it into space. Now, typically, you will find a lot of CubeSats riding on these SpaceX transporter missions. And SpaceX isn't actually handling the CubeSats directly. Typically, they are passing off, somebody else is actually buying like a launch on the transporter mission, and then their launchers will launch your CubeSats for you. But CubeSats aren't actually the smallest satellites that are launched by any means. In fact, I actually made a video a while back talking about the smallest satellites that have ever been launched. And yes, you can talk about the tiny copper needles which were launched as part of Project West Forward back in the 60s, which tried to create a ring that would reflect radio waves. I'm not talking about those. I'm talking about actually active pieces of electronics with solar cells and transmitters that can be picked up on the ground. And there was a guy at Cornell University who built really small things that were about the size of a large postage stamp. And I actually met him recently in Glasgow, and he showed me his stuff. He let me hold these beautiful little things. Obviously, the ones that he let me hold hadn't gone to space because those ones will have all burned up. But this was at an event called the Pocket Cube Workshop, and Pocket Cubes are smaller than CubeSats. They're like CubeSats that can fit in your pocket. They're actually done by the same guy, Bob Twiggs. He was the guy that created the original CubeSat standard. Well, he wanted to make them even smaller, and so he basically cut the size in half. And I actually get given a model. Actually, this is technically not even a model. This could legally be a Pocket Cube satellite. So it's basically 2 inches on each axis, or 50 millimeters, right? And if you can put your satellite into this volume, then you can then load this into a launcher, and technically it could legally be launched. Now, the company that does this a lot, that I was visiting with, was Alba Orbital. They're based in Glasgow. They've launched hundreds of Pocket Cubes, and they were the ones more or less running this CubeSat Pocket Cube workshop, right? And of course, you know, if you look at this, it does actually have their logo on it. So this is for them. Now, this is a 1P Pocket Cube. And one of the things you'll notice is, first of all, yeah, it's smaller than a CubeSat. The mass limit, I think, for this is 250 grams, as opposed to like a kilogram. But also you'll notice that there is a circuit board on the bottom, which is slightly bigger. This is a PCB. And that is intentional. That is part of the launch mechanism. So these go into a launcher, which has rails that grip onto these 2 side things, right? And they will pack multiple things in, typically 6 1P satellites get loaded into one of the Alba's launchers, and then when the door opens, there's a spring that pushes them all down the rails, and they all pop out into space, and now they're free to do whatever they want to do, to get loaded, have a good... No, wait, that's Primal Scream, right? They, another Glasgow act, right? So yeah, this is like the next step down. The cost is typically half that of a CubeSat. Sure, the volume is 1/8, but the cost to actually get to space for a CubeSat is something about $60,000 if you do it privately. NASA will of course launch them for free if you go via the educational route. If you do one of these privately, this is typically like $30,000 or 27,000 euros, I think. I don't know the exact numbers, but that's what it is to launch something this size. I have no idea what the exchange rates are these days. And anyway, so this is the 1p version. You can, of course, do longer ones, right? So they have the 2p where you extend it. You have the 3p. There's even someone that's made a 6p version. An interesting thing is that while these things add their volumes linearly, because the board is actually slightly longer, the board is 64 millimeters long. That means there's an 8 millimeter overhang at the end. If you do a 2p version, you get an extra 16 millimeters. If you do a 3p version, you get an extra 32 millimeters. So you get more like a 7-inch. You get an extra inch at the end. So anyway, with modern electronic miniaturization, you can do a surprising amount in something this size. Obviously, you can fit in your standard Arduino hardware and just make something that goes to space and acts like Sputnik and starts beeping out whatever. You can put a sensor on this. But what was really impressing me about this workshop was the ambition of some of the teams that have been doing really very, very capable pieces of hardware. There was a team that was discussing how they are working on orbital rendezvous between two of these extraordinarily tiny satellites. I think they were doing 2 or 3U versions, but they were having vanes that could adjust their position so that they would modify the drag, and by doing that they wanted to bring these spacecraft close together. There was another person working on solid state propulsion. So obviously these things have to be loaded into a launcher with other pieces of hardware, and they all have to play nice together. One of the rules is that you have to have like a dead man switch that detects the rail and will only power up the spacecraft once it leaves the rail. Obviously this thing is legal without a dead man switch because it doesn't do anything. As soon as you put any electronics in there, you have to make it inert. The hardware that it's made from, the materials, they can't off-gas because you don't want to contaminate your neighbors in the launcher, in the container. And you're not allowed any like compressed gases or highly energetic compounds, no pyrotechnics. So with that, how do you build a thruster that is viable? Well, this guy was presenting something called the solid state thruster. And it was beautiful in its elegance. It's basically anode and a cathode, and it's circular. And as the electric arc is generated, it jumps between the two and it creates a little crater. The arc jumps in, it creates a little puff of plasma, metal plasma, from either the cathode or the anode, I forget which. And that shoots off and generates thrust. So his promise was, you give me 1 watt for a day and your spacecraft will get 1 kilometer of altitude in orbit. So that's not bad when you're considering these levels of power that's available for these things. Now, obviously, to make that useful, the spacecraft would also have attitude control. His solid-state thruster, by the way, takes up 1/2 of this. So, like, it's 1 inch by 2 inches by 2 inches, and it all fits into here nicely. So yeah, what else? Another interesting thing, I was saying that you have to be inert, right? You can't have pyrotechnics, for example. Lots of modern satellites will use pyrotechnics for deploying various things, right? They'll have things that are held in place, and then once they're in space, they fire this, it'll pop something open, and then the panels will deploy or whatever. For satellites this size, you're not using pyrotechnics, but what you are typically using are something called burn wires. So you say you have an antenna. One of the most common things to do, build an antenna from, and when you're working on CubeSats, is a tape measure, metal tape measure, cut to the correct length, and then you fold it up, and when you release it, it pops out, because that's what tape measures do. But to hold it in place, you wrap a tiny fine piece of metal wire over that will hold it down. And then on your board, you have some contacts. And typically, you'll actually have some vias that go through the board with the contacts on the side, so you can wrap the wire around it. Once it gets out into space, once it detects that it's free and is able to deploy, you can apply power to those particular contacts, and electricity will flow over that very fine wire. The wire will get hot, melt, pop, and the wire comes out, and your satellite deploys its antenna or its solar panels. And so Alba Orbital, again, the people that had brought me out for this particular conference, they have what's called the Unicorn platform. And this is a stabilized platform that you can put your spacecraft, your hardware, your payload on. And it is a 3P pocket cube. One version of it contains a camera, and they demonstrated that this spacecraft can actually point at the Earth and take photos, and I'll explain how it does that. But they can also just take your particular payload. So it's like a 3P version, and right at the back, that is where most of their hardware is. At the front, you can build your hardware and put it on a series of these small boards. So these are like 95 by 46 millimeters, and you can stack apparently up to 6 of these boards, which are populated inside that cabinet. They can provide up to 20 watts of power because they fold out solar panels, 4 sets of solar panels on either side. Obviously, they go through with a burn wire to take those out. They also deploy an antenna at the front, and the antenna comes up and it kind of looks like a horn, which is why I think they call it a unicorn, maybe? It could just be that unicorn is like big part of Scottish mythology, so you know it's part of the like Glasgow University coat of arms and everything. But so you can build a camera platform, you can build something else that does Internet of Things. But I was very impressed because they gave a presentation essentially talking about their attitude, determine, and control system that they have in a spacecraft which is 7 inches long, right? less than 20 centimeters long. It will adjust itself. Once it comes out, it will correct, it'll cancel out the tumbling. It will then align its solar panels to the sun. And if it's the camera version, they demonstrated that they can bring it out of this attitude and point it opposite the sun at the right time. So you figure out when the target you want to photograph is going to be opposite the sun. You have about 30 seconds it takes to turn it over, snaps the photos, and then you can bring it back to the other position relatively quickly. And so I visited their little factory, and I got to see how their launchers work. They actually gave me a demo how the launcher works, and the satellites on their test launcher just disappeared across the room in somebody's desk, underneath somebody's desk. But they showed me the internals of their attitude control system, and it was extraordinary that they could shrink an attitude control system down into this tiny volume. So they have 3 sets of magnetorquers that will sense the magnetic field and react to the magnetic field to remove any rotation. So you have 3 of them at 90 degrees to each other. And then they have 3 reaction wheels. Reaction wheels on a spacecraft in this volume. I mean, this is it. The functional volume, roughly this size, contains the attitude sensing, it contains the reaction wheels, and then there's some sensors on the outside. So I guess what I'm saying is it is extraordinarily impressive that you can build small satellites in this form factor. So Alba, I think they've launched on a bunch of different rockets. Initially, they went up on Rocket Lab, running out of fingers. That was launch number 10. And since then, they've mostly been on SpaceX transporter missions. And I think they have been so they sell their payload space to another company, and then they buy their payload space off of somebody else who then ultimately buys it off of SpaceX. You see, there's middlemen all the way down when your satellites start getting very, very small. The great thing about pocket cubes is that, like CubeSats, there's a thriving open source community that lets you use reference designs. It lets you work through them and use the experience that someone else has already had, and then use that to build and inform your own hardware. You might remember last year that Mark Rober, they did a big thing where they launched a satellite into space, a selfie satellite that would take pictures of a screen, and you could like upload your own photos and see your photo floating in space. What wasn't mentioned at the time was a Polish group had done that previously earlier in the year. Poland can into space indeed. That was one of the things they displayed on their little screen. And they had used a pocket cube, which, was as their platform. So in the factory, I also got to see their vibration test platform, where if they get customer payloads, they can stick them on this, verify that they're able to handle the vibration expected during launch. They had their attitude control platform where they were testing this. And so they have this air bearing that they can put their satellite on and start it spinning. And it's inside like a Helmholtz coil, so they can control the magnetic field and simulate the magnetic fields it would experience in orbit. They can add light to make sure that it is tracking the sun correctly. And I watched as this thing that started spinning was able to, over a couple of minutes, slow itself down using the magnetorquers. And then once it had slowed down enough, you could see the reaction wheels slow down and start to adjust its position until it finally aligned with the sun. And then, of course, we could move the sun around and mess with its head, and it would faithfully track the sun. It is beautiful to watch a satellite that is this size performing this kind of motion and know that they are actually able to do this on orbit. Now, another part of their thing that they showed me was their trailer that they were using for receiving this on the ground. Obviously, one of the interesting things with the pocket cubes is they are sort of right at the limit of what the Department of Defense is able to do in the US in terms of tracking. So sometimes they get lost. The smallest objects imaged on orbit apparently have been, pocket cubes, which is kind of impressive that you can see something this size from 200 kilometers or more away. If it's just basically catching the sun just right and reflecting it, it can be visible. But yeah, using their receiver, they are able to wait for it to come across the horizon, and once they get locked on, they're able to download at 200 kilobits per second, which is more than enough to get down fairly large images that they've taken with their spacecraft. And so they shared a number of images at this event, at this conference. Again, it's very cool to see a lot of this stuff. Another very cool thing I saw at this conference I kind of want to mention is the tiny telescope people who have this demonstration. It's a solid lump of glass which has been ground into a very tiny little telescope, right? So it has a corrective lens on the front. It has a reflector at the back, which reflects up to a secondary, which is ground onto the front and silvered, and then that emerges out the back. And this is able to get very high levels of zoom from a very, very small package. It's rather beautiful, and you can see why they would be demoing this at a satellite for tiny spacecraft. Now, that is not what Alba's Unicorn is doing. Alba's Unicorn is doing something completely different. Now, we should mention that Planet, of course, started their business with their Dove satellites, and those are built on 3U CubeSats. That means that their lenses are twice the size. That means they need 1/4 of the exposure time, or they can get higher resolution. The resolution that's possible from a lens of this size is something we can calculate based on Rayleigh criteria, which is like an optical limit based on diffraction patterns. If you have a 50mm wide lens, then the Rayleigh criteria tells you that that is able to resolve down to 2.76 arc seconds, so about 3 arc seconds. What does that translate into? Well, in a 400-kilometer orbit, that is about a 6-meter resolution is the absolute upper limit of what you can get. 12-meter resolution is more likely. So if you have, say, a scientific need for imagery that's 6 to 12 meters of resolution, you can build a satellite that can literally fit in somebody's pocket, that can go to space and gather that for you and do your specific task and needs. So yeah, I've had this sitting at the back of my office for the last month or so, and I really kind of just wanted to talk about the things that I saw at this event and how they are really, really cool. I met a whole bunch of people trying to build stuff that fits into this form factor or slightly larger form factor. They are doing amazing things, and literally, if you have the time, the energy, and the ingenuity, the sky is not the limit. You can go to orbit. I'm Scott Manley. Fly safe.